In this video, we'll talk about perfect complements, which is actually characterized by the consumer wanting to consume two goods together, thus being complements. The example that several textbooks use is the left shoe and the right shoe. A consumer's utility will only increase if he is given both left and right shoes. If the consumer has, for example, a lot of left shoes but no right shoes, then he cannot use the shoes at all. So his utility will not increase. In this case, the only way that the consumer can increase his utility is if he or she consumes in a certain proportion. And if we map that out on the indifference map, let me draw the indifference map here. If we map that out on our indifference map, what we will see, and this is x1 and this is x2, what we will see is a letter L. So the consumer's indifference curve looks like a letter L. Let me draw another level of utility here, right above here. And what we can see here with intuition is that if the consumer consumes just 1 unit of x1 and 1 unit of good 1 and 1 unit of good 2, he would have a utility of u naught. And if he does increase his consumption of good 1, so if he increases his consumption of good 1, but not of good 2, he would still be on the same indifference curve. On the other hand, if he consumes more of good 2, then he would still remain on the same indifference curve. Only when the consumer increases his consumption of both good 1 and good 2, so both good 1 and good 2, does he or she increase his utility. In this case, the utility function of our consumer is represented by u as a function of x sub 1 and x sub 2 is equal to the minimum of a x1 comma b x2. And as we already know, x1 and x2 are quantities of good 1 and good 2, and a and b are just constants. The minimum operator over here, the minimum means that the consumer gains the utility equivalent to the smaller of the two numbers. So, given this example, say the consumer needs two pens for one notebook. I'll just write this in a ratio form, notebook. So for every 2 pens, the consumer needs 1 notebook to use up the 2 pens, and for every 1 notebook, the consumer needs 2 pens to fill up the notebook. So the consumer consumes a ratio of 2:1 for pens to notebooks. If the consumer, for example, has 24 pens, if the consumer has 24 pens and 20 notebooks, he would only get the utility equivalent to 24 pens and 12 notebooks. So 24 pens and 12 notebooks. In this case, the 8 notebooks will actually not contribute to his utility unless he has more pens because the notebooks are rendered useless. Let us say that for every 2 pens and 1 notebook, the consumer would get 1 unit of utility. So we will assign x sub 1 as the quantity of pens and x sub 2 as the quantity of notebooks. So in this case, the consumer would need 2 pens for 1 utility. And so 1 utility would need 2 pens. So 1 pen would actually give just u over 2 utility. And this can actually be rewritten as 1 over 2 u. And 1 over 2 here is the value. 1 over 2 here is the value for a. So a is actually equal to 1 over 2. On the other hand, 1 notebook would give 1 unit of utility, so b would just be equal to 1. So now we can actually use our utility function to find how much utility 24 pens and 20 notebooks actually give our consumer. So let me just scroll to the right. So u, which is a function of x sub 1 and x sub 2, would now be equal to the minimum of a is, in our case, 1 over 2, times x sub 1, which we already stated that it's 24. 24, comma, b in our case is equal to 1 times 20, because we have 20 notebooks. Close parentheses. And when we multiply this, when we solve the equation, what we find is we look for the minimum, or the smaller of the two numbers, when the first number is actually 1/2 of 24, so that is 12, and the second number is 20. 12 is actually smaller than 20, so the utility that 24 pens and 20 notebooks gives our consumer is simply 12 utility. And what we see here is that the consumer actually has too many notebooks. And in order to increase his utility, the consumer actually has to consume more pens because he has a surplus of notebooks. But what if the consumer already had a budget allocated for pens and notebooks? So the only way that the consumer can increase his consumption of pens is to decrease his consumption of notebooks. So to maximize utility in the case of perfect complements, A, x1 should actually be equal to B, x2. This way, as we increase our consumption of good 1, we decrease the consumption of good 2 until the minimum of the two numbers becomes as large as you can possibly make it. So again, AX1 should be equal to BX2 to maximize perfect complements. Now in this example, I want to explore or show how the consumer should behave given a budget constraint. So again, let us say that the consumer gains 1/2 utility per good 1 and 1 utility per good 2. And this is our utility function in this case. So u as a function of x sub 1, this is u, x sub 2 is actually equal to the minimum of 1/2 x sub 1 and 1x2. Subject to, so the consumer this time has a budget constraint, m is equal to p1 x1 plus p2 x2. And so what we want to do is to maximize utility given this utility function and this budget constraint. So what we're going to do is first see to it that we are following the condition that A x1 is equal to B x2. And the way to do this is simply by getting the information from our utility function. And so here, in this case, A is actually equal to 1/2. So 1/2 x sub 1 should equal 1 x sub 2. And so we try to isolate either x sub 1 or x sub 2. So in this case, it's easier to isolate x sub 2 because 1 times x sub 2 is just x sub 2. So x sub 2 should be equal to x sub 1 over 2. And given this value, we want to plug this in to our budget constraint. And so m would now be equal to p1 x1 plus p2 times x2, which we found was actually equal to x sub 1 over 2 when we're trying to maximize utility. And now what we want to do is to isolate x sub 1. So x sub 1, we can factor out x sub 1 here. X sub 1 multiplied by p1 plus p2 over 2. And so x sub 1 should be equal to m over p1 plus p2 over 2. And there we have it. Again, what we're doing here is just trying to find the maximum of the utility function subject to a budget constraint.